Okay, so once you've learned the basic gas laws that are dealing with various aspects of pressure, temperature, and volume, you're ready for all of those conditions to be combined. And the first way we're going to go over that is the, well, not very creatively named combined gas law. And the combined gas law is going to combine Boyle's, Charles, and Gay-Lussac's laws. And the important thing to remember in the combined gas law is we're looking at changing conditions, meaning that you have an initial set of conditions, which we typically refer to as 1, and then you're going to turn into some final set of conditions, which we tend to label condition 2. So the only thing to remember here is that, again, temps must be in Kelvin, that your pressure and your volume must be, so your conditions 1 and 2 must be in the same unit. So the thing you're going to recognize when you are looking at these problems is that you are going to have multiple pressure, volume, and temperature values. So you're going to end up having lots of givens, which can be kind of confusing, but not if you recognize that you are just looking at multiple number 1s and multiple number 2s. There is one exception to that, and that is if you read a problem that's talking about standard temperature and pressure, otherwise known as STP. We've covered STP before. We talked about that at STP you have 1 mole of gas equaling 22.4 liters of gas. So we looked at that during stoichiometry, but here those letters are actually telling you conditions. So they're giving you the initial or the final conditions, but they're doing it in word form. So the thing to remember, standard temperature, 273 Kelvin, and remember that is very cold. For us, that would not be the kind of conditions you'd have in a lab because you'd need a coat, and that those pressures are 1 atmosphere. And the 1 atmosphere is also, of course, the same as 760 millimeters of mercury or 101.3 kilopascals. And this is sea level pressure. And this is very standard lab conditions, right? I mean, this is what most things are going to occur in. Okay, so up here I've put up our 3 gas laws. So pressure and volume, that's Boyle's. Volume and temperature, that's Charles. And pressure and temperature, that's Gay-Lussac. So we're going to create the combined gas law here. So the first thing I'm going to do is for the left side of our equalities, anything in the numerator, I'm going to put a box around in red. So pressure and volume 1 are on the left side numerator here. Volume 1 in the left side numerator here. Pressure 1, left side numerator there. And then let's switch colors, and in blue, I'm going to do the left side denominator. Well, in Boyle's law, there is no left side denominator. In Charles, left side denominator is T1, and in Gay-Lussac, the left side denominator is T1. Switching colors again to black, let's do the right side numerator. So in Boyle's, that's P2, V2. In Charles, oops, that should be a bar right there, so it's V2. And in Gay-Lussac, it's P2. And then lastly, let's do the denominators. There are no denominators in Boyle's. Denominator of T2 in Charles and T2 in Gay-Lussac. So if we combine all those things, let's pull all of the left side numerators together, and that is P1 and V1. All right, that covers these, this, and this. And then the left side denominator, T1. That covers this and this. Right side numerator, P2, V2, that covers this, this, and this. And right side denominator, T2, that covers this and this. So this right here, this is the combined gas law. And as you can see, it literally is all three of those gas laws combined together. So the combined gas law is P1V1 over T1 equals P2V2 over T2. So again, we normally think of the ones as the initial conditions and the twos as the final conditions. So you can rearrange all of these things to be able to solve for each one. So let's start with P1. Well, that's P2V2 over T2. We already know that. T1 was in the denominator, so now it needs to be in the numerator. And V1 was in the numerator, so it now needs to be in the denominator. V1 is going to look exactly like that. E2V2 over T2. So same thing, T1 is going to be in the numerator and P1 will be in the denominator. And then if I have T1, well, that one looks a little different. So again, you can do that cross multiply thing. So T1 is going to be equal to P1 V1 T2 divided by P2 V2. Okay, and then if I'm trying to get P2, very similar, P1 V1 over T1. Let's see here, the T2 was in the denominator, so now in the numerator. The V2 was in the numerator, now in the denominator. Same thing, V2, we've got P1 V1 over T1. T2 in the denominator, so we now put it in the numerator. V2 in the numerator, or P2 in the numerator, we now put it in the denominator. And lastly, to get T2, we're going to start off with P2 V2, and then to so your T1, and then we're going to end up dividing that by P1 and V1. And for that cross multiply thing, let me do that over here. So if I have P1 V1 over T1 equals P2 V2 over T2, I'm going to take this and cross multiply it up there. I'm going to take this and cross multiply it up there. And that will give me P1 V1 T2 equals P2 V2 T1. And then you can see how I got to here. I simply divided both sides by that P2 V2, and that's what gave me that formula. And to calculate or to get the T2, I simply divided both sides by the P1 V1. So the thing to note is that temperature will always be next to the other number of condition for pressure and volume. In every single one of these, the temperature value is with the other number. So this T1 is with P2 and V2. This T2 is with a V1. Always. T2 over here is with the ones. T1 is with the twos. All right, this 1 is with these twos. Right, this 2 is with these ones. The temperature is always going to be the outlier. Okay, so let's do a problem. All right, once upon a time, the economy size, 325 milliliters, that's a volume, can of Big Brute aerosol deodorant contained a propellant gas at 445 kilopascals and 12 degrees Celsius. That is one sentence. That means all of those values go together. So V1, kilopascals is a pressure, T1, 12 degrees Celsius is a temperature. So what volume Would this propellant gas occupy if it were allowed to escape into a 101 kilopascal and 21 degrees Celsius environment? Well, that's a new pressure, and that is a new temperature. So I'm being asked to find a new volume. That's my question, all right? So V2 is what I'm being asked to find. So let's kind of see if we can logic anything out here. So my temperature went from 12 up to 21. So my temperature increased. And my pressure went from 445 down to 101. So my pressure decreased. So if we're looking at this, if temperature increases, what do we expect the volume to do? Well, we would expect the volume to increase. And if the pressure decreases, what do we expect the volume to do? Well, Boyle's law says that those are inverse, so we would also expect the volume to increase. So overall here, both of those things, we are looking at a volume increasing. Those are both happening in the same direction. So we're going to solve for V2. So we know that that formula, V2, let's see, it was P1 V1 over T1, and then I moved over the T2 and the P2. So I've got all of that. Now, kilopascals, those are the same unit, so I'm ready to go with my pressures. Milliliters, well, that means my volume is going to be in milliliters as the final answer. That's fine. My temperatures are in degrees Celsius. I have to adjust those. So T1 started off as 12 degrees Celsius. I need to add 273 Kelvin, and that is going to give me 285 Kelvin. And for my T2, that started off as 21 degrees Celsius. I need to add my 273. Let's see here, 294 Kelvin. So now I have my temperatures. So I can plug everything in. Now notice I have 3 things in the numerator and 2 things in the denominator. You can write these numbers down correctly, but if you do not put them in the calculator correctly, you will not get the correct answer. So I'm going to write it down the way you should enter it. So open a parentheses, your first pressure, 445 kilopascals, times your volume, 325 milliliters, times your second temperature, 294 Kelvin. Now close your parentheses, divide it by, open another parentheses, your T1, which was 285 Kelvin, times your P2, which was 101 kilopascals. Close parentheses, then you'll hit equals. So my kPa cancels out, my Kelvin cancels out, and I am left with milliliters, which is good because it's a volume question. So when you plug all of that in, you're going to get a number 1,477.150 milliliters. Okay, so let's talk significant figures. So the temperatures here were both additions, and those additions leave me with 3 significant figures. My pressures were both 3 significant figures. My volume was 3 significant figures. So I should have 3 significant figures. So what do I have to do? Well, start from the left. The 1 counts, the 4 counts, the 7 counts. But I need to chop it off here. However, this decimal place means I have to maintain a placeholder 0. So I'm going to have a 0 go right there before my decimal. But what does that 7 make happen? Well, it makes this go up and it makes that become an 8. So my answer is 1,480 milliliters. And that's how you do a combined gas law problem.